Hi friends, I am Dr. G. Srinivasa Gupta, Professor in Mechanical Department of VIGNANA JYOTHI Institute of Engineering Technology. As part of dynamics of machinery, today we are going to discuss a simple band brake concept. So far we have seen in previous lectures that types of brakes, mechanical brakes especially, two are a block brake or pivoted block brake or double block brake, and now we are going to discuss simple band brake. We have seen that the difference between shoe or block brake and pivoted block brake. Shoe or block brake, the shoe or block is rigidly fixed to the lever that is come in contact with the rotating drum. Due to frictional resistance, brake is going to be activated. In case of pivoted block brake, we have seen that the block is not rigidly fixed to the pivot, and in that case the equivalent coefficient of friction is estimated using the relation mu dash equal to 4 mu sin theta by 2 theta plus sin 2 theta, that we need to use for our braking torque and frictional force calculation. And double block brake, as we have seen, the side force thrown on the shaft leads to bending of the shaft, that can be eliminated because of the moment due to the normal reaction from both the blocks can be neutralized on the pivot. So there is no bending action of shaft, that can be eliminated. Now today we are going to see simple band brake. What is it? The name itself indicates band. This is the brake which contains friction brake, all are friction brakes, in which a flexible band or belt made of leather or steel wire aligned with the friction material is wrapped partially around the circumference of a rotating drum. When the band is tightened, friction between the band and drum produces braking torque, that is frictional force or frictional resistance that leads to braking torque. The principal working principle of this brake is simple. The frictional resistance between the band and the drum, rotating drum. Okay, so you need to understand some important aspects of this brake. Brake drum rotation. Drum is attached to the rotating shaft of a machine. Okay, flexible band around the drum, that is wrapped around the drum, over a certain angle of contact, whatever that angle of contact we will see. And application of force. When force is applied through the lever, then it exerts a tension on both ends of the band. The tension difference leads to effective force applied. Then that force leads to frictional resistance. Okay, that friction between band and drum surface produces resisting torque. So then the motion is retarded or it may be stopped, depends on amount of frictional resistance exists when we apply brake. So the basic principle and the important, this is like a belt drive concept, because two ends of the belt are in different tension at tight side and slack T1, let us say slack side T2. Then the tension ratio derivation we have seen previous topics, belt drives. Then that is T1 by T2 equal to tension on tight side T1, tension on slack side is T2 equal to E for mu theta. Mu is coefficient of friction between band and the drum, and the theta is angle of wrapping angle. Okay, so this the configuration, how the band is wrapped around the wheel or drum is in this case it is like this: steel or leather or belt which is wrapped around the drum. On this one end belt is wrapped. This is the belt. Okay, one end of the belt is pivoted at let us say A, and other end of the belt pivoted to the lever at B, let us say. Then drum radius as usual R. Okay, then if you observe the effort, if at all required, we need to apply on the lever end. Then if the drum is rotating clockwise, then obviously the tension tight side becomes, this is the tension on the drum, on the lever it is tension. Okay, on the other hand, similarly it becomes slack side if drum is rotating clockwise. Okay, slack side tension is T2. Okay, so I am showing on the lever what is the tension of the band ends, and on drum if you take what is the tension on the band ends. Similarly, it is rotating anti-clockwise. This tension tight side become this side, and slack side become at B on the band. Okay, so these terminology is as usual. T1 tension on side side, T2 tension in slack side. Okay, mu is coefficient of friction between drum, and theta is contact angle. So what is braking torque? Braking torque is tight side tension T1 minus slack side tension. This is tension means force, tensile force on the belt into radius of the drum. Okay, if you say radius of the drum R, okay, as it mentioned here, then this is the braking torque. Okay, this is simple band brake, and other types of differential band brake and band and block brake combination also we can have. So now coming to the application of these band brakes, we are going to see how the tension ratio T1 by T2 equal to per mu theta can be derived also. Okay, so before that let us see application of band brakes. Band brakes are used in systems where moderate braking torque and simple construction are required. This is very simple construction. In case of coming to practical applications in hoisting and lifting machines, cranes, hoists, winches, and conveyor systems also this is used in industries, and in elevator and lifts also this is used as a braking mechanism, and agricultural machinery and marine equipment, and small industrial machines also, rolling mills, machine tools. These are the applications of this simple band brake. Okay, advantages, it is construction is simple, very simple. So obviously cost is so less, and maintenance is easy, and high braking torque for small effort can be applied, because the tensions, if we make it difference, then that is the effective force. Then braking torque we can have more. Okay, only the disadvantage of this is band wearing, band lining wear is more. Okay, heat generation may be, if you use continuously the braking, heat may be generated more. Okay, braking depends on direction of rotation also. These are the some disadvantages. Okay, so braking torque, how we derive? If we take this is the drum, okay, this is the band, let us say tight side and slack side. If it is rotating clockwise, this is the tight side T1, this is the slack side T2. Okay, then this is the wrapping angle. Here it is starting contact. Here it is okay, starting contact and ending contact. Let us say because T1, T2 we are coming clockwise. Then this is the angle 2 theta or theta. Let us say wrapping angle. Okay, then what is the braking torque? If I take small length of this band, and it is making an angle with the okay, this is the d theta. Let us say with this drum. Then okay, then what is this this band width is B if I say, and thickness is T, then this is radius or drum. Okay, then I can write force acting on the band. Okay, that is we can see that okay, tension I am taking here T, and this is T plus dt, the difference, small band I have taken, T one side, T plus dt, other side, difference is dt. Okay, then we have this dt is the difference, then normal reaction between band and drum, because of this normal reaction and band and drum. What is that normal reaction? Because effective dt is the effective tension. Then normal reaction we want to see. What is that normal reaction? We can write that is dn. Let us say normal reaction is dn. This is the dn. Okay, I am showing this is the belt length we have taken on the drum. This normal reaction is dn. Then the torque, because of this dn, the torque, the frictional force. The frictional force, if you want, dF equal to mu dn. As usual, normal force, frictional force on the small contact area is dF equal to mu dn. Then what is dn? First of all, dn is, we can see, you can write dn is, this is the dt. So dn we can write dn equal to t d theta. Dn equal to t d theta. How it can be written? I will tell you. Need not worry. Here, okay, I will draw here. So because this is the, okay, drum, and this is the small we have taken. Here, if you take this much length, let us say T is the tension here, we said, on the small element, and T plus dt is the tension this side. So this normal force, okay, okay, this normal dn. So dn, okay, if you take equilibrium forces in vertical direction, then you can see that what is this angle. If you draw tangent here, what is this angle? This angle also d theta. Is it or not? D theta. Okay, d theta by 2. Okay, let us say here also d theta by 2. This angle. Then if you take vertical direction, all the forces equilibrium, this is acting upwards, this is also upwards. Okay, because of t, this is d theta. So what is this dn equal to dn downwards and t plus dt sin d theta plus t sin d theta. Do you agree? Okay. Then if theta is very small, d theta is d theta, and dt and d theta product is very small. D theta by 2 actually I have to write. This is d theta by 2, this is d theta by 2. Okay, d theta by 2. Okay, so then, okay, d theta, sin d theta by 2 very small, then we can write it is equal to d theta by 2. So dt and d theta by 2 multiplication is very, very small compared to other terms, then we can neglect that. Then t d theta by 2, t d theta by 2 is the summation dn equal to, then t d theta. Okay, I think you are able to understand. Dn equal to t d theta. So dt we know that. Okay, dt is we have already seen dt by t. We have seen already mu d theta. Okay, because yeah, how you are going to achieve dt is mu dn, you know that. So dt is equal to mu t d theta, because dn is t d theta, you substitute mu t mu t, dt equal to mu t d theta, dt by t equal to obviously mu d theta. Okay, mu d theta. I think you are able to understand how we are arrive this dt equal to mu t d theta, dt by t equal to mu d theta. Okay, so if you integrate both sides, what are the integration limits for t? T integration limits, you know that maximum tension T1, minimum is T2, and that is slack side, tight side T1, and dt dt equal to theta. Theta is starting from 0, whichever side you are taking, 0 to whatever theta that angle, and mu d theta. From this you can understand, okay, it is dt by t, not dt. Okay, so then it is log t1 by ln t1 by t2 equal to mu theta you will get. Then of course you apply anti-logarithm both sides, t1 by t2 you are going to get e power mu theta. This is the relation derived in belts also, okay, belt drives also. So T1 by T2 is e power mu theta. This is belt friction equation used in band brakes. Okay, this is called tension ratio, tight side tension to slack side tension, that is e power mu theta. This is one relation. Then if you know frictional resistance, then frictional resistance, what is that? Effective force is T1 minus T2. Okay, this is effective force. This force into this is effective tension. Then this effective tension into R. Okay, R is torque. torque, braking torque. Okay, effective tension T1 minus T2, that is effective tension into R braking torque. Okay, this is the braking torque you can calculate using this relation. Okay, are you able to understand? I think braking torque you can evaluate like this. So finally, braking torque is T1 minus T2 into R, and tension ratio is T1 by T2 into equal to e power mu theta. From these two, using these two relations, in any given problem with the given specifications, first we need to evaluate T1 and T2. Okay, for known values of coefficient of friction and angle of wrapping angle, okay, and radius of the drum. Once you evaluate this, suppose you want effort required to apply the brake P, then you take moments. This is the belt wrap, okay, this is the drum, this is the point, let us say A, okay, pivoted, and here it is pivoted at B. Then if you know this distance, okay, this distance, let us say L1, total length of the lever, if I take okay, L, then you can take moments about this pivot A, then you can write the P into L equal to this. These are the tensions here. If it is rotating clockwise, T1, okay, T1, T2, T2. Okay, you can take moments about A, let us say, then T1 won't come into the picture, T2 won't come into the picture, T1 into L1, okay, equal to P into L, because this is opposite direction, this moments. Then you can write P, okay, P equal to T1 L1 by L. Okay, I think you are able to understand the relations. Okay, this way you can find effort if it is required. So what are the key important understanding required here is band brake works on friction between band and drum. Tension varies exponentially along the band. I have seen the relation T1 by T2. So maximum braking torque depends on coefficient of friction, angle of contact, drum radius, and applied force. So this is a very simple understanding of this band brake. We will see some numerical exercise on this, as well as other types of band brake, differential band brake also, and band and block brake, the combination of these two in coming lectures. With this, and one more thing, the difference between band brake and block brake, as we know that already we have seen in previous lecture, block brake. So construction wise, here band is used, flexible band, and in block brakes, rigid shoe pressed on drum. Here because of tension difference, first one band brake, here because of frictional resistance, directly shoe is contacting with the drum, and contact area is large contact area you have observed here in band brake. That's why more effective frictional torque can be we will have, and a smaller contact area in block brake. And frictional principle, belt friction, tight and slack side, that is belt tension ratio, that is tensions difference, that will give braking torque. And direct normal force which leads to mu into that normal force is braking resistance, okay, frictional resistance. Okay, braking torque equation, okay, this is T1 by T2 is e power mu theta 1, and T1 braking torque equal T1 minus T2 into R. Using these two relations we can find tensions on tight and slack sides. Okay, and we can have in this case braking torque is equal mu into normal reaction, that is Rn, and sensitivity of direction depends on direction of rotation. We will have braking torque, and in the case of this block brake, less depends on direction. Actually we have seen that also. Heat dissipation, because more contact area, poor for continuous braking, and better heat dissipation, less contact area. Okay, so where band lining wears along length and shoe line wears at contact area. And construction complexity, simple band brake and slew brake, slightly more rigid design is required. Okay, applications we have seen. Okay, this is shoe brake applications. We know that these are simple vehicles, generally automobiles, so we are going to use. So these are the application wise you can see: block or shoe brake, automobile drum brakes, elevators, machine tools, industry machinery sometimes. And but in case of band brake, cranes, hoists, wrenches, conveyors also, material handling equipment, wherever it is. These are about these applications. and the difference between band and block brakes. So with this, I am concluding this lecture here. Next coming lecture, we will see some numerical exercise as well as the other types of band brakes, differential band brake, block and band brake. Okay, thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.